Alright, hello everybody, and today we're going to be solving this weird looking integral right here. So I already called the integral I just so you know what we're solving later on. But yeah, let's just jump straight into it. So let's take a look at this function in here first. Notice that we have this e minus 1 in the exponent sitting there for no good reason. And we have this natural log of x in the denominator, which is quite disgusting. So why not first of all try to get rid of this e minus 1, and just bear with me here. We're going to define a new function. So we're going to let some new function, let's call it f of t, be equal to the integral from 0 to 1 of x to the t minus 1 over natural log of x. And notice I've parameterized this exponent of the x here, and that kind of takes care of this e minus 1, because notice this is a function in terms of t. So if we let t equal to e minus 1, well then we're just going to get our original I back. So just plugging e minus 1 into this t here will get us our original I back. So I hope you agree with that statement. And I forgot a dx here. So now let's try and get rid of this natural log somehow. Notice this term right here, this x to the t. How can we generate some kind of natural log maybe to cancel it out? Well, notice that if we differentiate x to the t with respect to t, what we're going to get is the original function itself times an extra factor of natural log of the base. Let's say x like that. So it's kind of like taking the derivative of e to the t. You're just going to get your original function back times an extra factor of natural log of the base, which is e, but natural log of e is just 1. So derivative of e to the t is just e to the t. So maybe we can take advantage of this to deal with this integral right here. So why not differentiate our function f in terms of t? So if we take f prime of t, well that's just the derivative of this integral. And using the Leibniz rule for differentiation under the integral sign, we can bring this differential operator inside of the integral. So what this becomes is the integral from 0 to 1 of the partial derivative of x to the t minus 1 over the natural log of x dx. And this natural log here is independent of t. That means we can bring it out to the front. So now we have the integral from 0 to 1 of 1 over the natural log of x, partial derivative of x to the t minus 1, and taking the derivative of this x to the t here, well that's just this thing right here we found earlier, and the derivative of a constant is just 0, so we can ignore that. So now we have the integral from 0 to 1 over natural log of x, and then derivative of x to the t becomes x to the t times the natural log of x. Then we have dx right here. And notice natural log of x here and natural log of x here cancels out, and what we're left with is the integral from 0 to 1 of x to the t dx. Alright, and now we can just simply take the antiderivative of this thing and evaluate it at its bounds. So now we have 1 over t plus 1, x to the t plus 1. So this thing here is just the antiderivative of x to the t, and we want to evaluate this thing from 0 to 1. Well, notice if you plug 0 into this x here, and notice this integral is with respect to x, we're just treating t as a constant in this case. So if you plug 0 into x here, well 0 to the anything is just 0. So you can ignore this 0 right here. And if you plug 1 into x, well 1 raised to anything is just 1. So all we're left with is 1 over t plus 1. And remember, this thing here is only the derivative of f in terms of t. But what we want to find is f of t. So how do we get from a derivative to the function itself? Well, all we have to do is anti-differentiate it again. Alright, so continuing on here, we want to find f in terms of t. So f in terms of t is the same as the integral of our f prime of t integrated with respect to t. Alright, but this is just the integral of 1 over t plus 1 dt. And this is just, if you just do a bit of chain rule in your head, derivative of this denominator here is just 1, so you can just treat the whole denominator here like a single variable. So you just get natural log absolute value of t plus 1. And also notice we also have a constant because we're integrating without bounds. So now this thing is our f of t. So what do we have so far? Well, on the one hand, our f of t is equal to the natural log of t plus 1 plus some random constant c. But notice, as we defined earlier, that is also equal to the integral from 0 to 1 of x to the t minus 1 over the natural log of x dx. Well, how can we figure out what our constant is here? Well, maybe we can do a smart substitution for our t, because if these two expressions are equal, that means for any value of t it takes in, well, the two expressions must still be equal. So why not let t be, for example, 0? So if we let t equal to 0, well, what will happen to our natural log of x? Well, we're only going to get natural log of 0 plus 1, which is the natural log of 1, but the natural log of 1 is just 0, and we're adding our constant here. And what happens when you plug 0 into our integral here? Well, x to the 0 is just 1, and notice we have a negative 1 here, so we have overall 1 minus 1, which is 0, and 0 over anything is just still 0. And if we take the integral of this thing here, which is 0, well, we're just going to get 0. So 0 plus z equals 0. Well, if you subtract 0 on both sides, that means c equals 0 minus 0, and 0 minus 0 is 0, so therefore our c equals to 0. So in the end, our f in terms of t is equal to just the natural log of t plus 1. But remember, from the very start, we wanted to find our I, which was our original integral we wanted to evaluate. But our I, we noticed that it was just our function f evaluated at e minus 1. So why not plug e minus 1 into a function here and see what we get? So since our I is equal to f evaluated at e minus 1, therefore our I is equal to the natural log, and t, we're replacing that with e minus 1, and then plus 1, negative 1 and 1 will cancel, and what we end up with is natural log of e, but the natural log of e is nothing but 1. So our final result for our integral is just 1. So I hope you guys enjoyed this quick little video, and I'll see everyone next time.